Hi guys, today I wanted to talk to you about the differential differential reading with an op-amp, because the problem in power electronics, for instance, when you have a buck converter, let me draw a buck converter just for a moment. Here you have the inductor. You have the switch Q1 and the switch Q2. You have the inductor L. Now, if you wanted to read this current, the problem in this is how can you read this current? You have to put a shunt resistor, which we call RS, and you have to read this voltage across the shunt here. And how can you do that? Well, in order to read safely this voltage, because it is very noisy, the first thing that you want to do is to design a differential low pass filter, possibly passive, which is something which is a combination of resistances and capacitors. Let's just design the system by a system. Let's just design the electronics with a system point of view. And now, after that, you have to design the differential op-amp. And you generally do that in order to eliminate the common mode, like this. So, remember that this is the resistor R1, R2, R3, and R4. This is the minus and this is the plus. Now, if this is V1 and if this is V2, the voltage read at the end of the story, if R1 is equal to R2 and equal to R3 equal to R4, or better, the configuration needed to eliminate the common mode is R1 over R3, which is equal to R2 over R4. This configuration cancels the common mode, which is extremely important in this kind of measurement, and the voltage VB, VO, will be equal to V2 minus V1. Naturally, if you decide to change the gain, and the gain, you can design the gain by changing the ratio between R1 over R2, naturally you have to insert the gain R2 over R1 if you want to design the gain. But generally speaking, you don't want to put so much gain here, because you're going to amplify everything which enters to it, so even noises. And so now, if you have this if you have the inductor current, now I'm going to teach you why you're reading actually the current. The voltage droppage here before the filtering, let's call it VK. VK will be equal to RS times IL. So, if you assume that Vk is basically equal to V2 minus V1, because it is just the filtering stage, you can safely assume that V0 is equal to RS IL times again G. And so what you're reading now is the inductor current translated in the voltage, which you can use for your control system or whatsoever. So in this video, I will show not only how to design this with all the characteristics, but also with a real measurement of the differential. So let's start. The first thing that you want to use is the Universal Opamp 2. And in the Universal Opamp 2, just put a voltage of plus and minus 10 volts. Let's call this node V plus, and let's call this node V minus. Let's transfer the nodes here, V plus and V minus. Now let me call the resistor R1, R2, R3 and R4. And just for simplicity, let me put everything to 1 kilo ohm. Now, let me put V1 and V2. So we expect the output voltage to be V1 minus V. What? Oh my. Let me wait. Just wait a second. Okay, so before going on, let's actually test. So let me put a voltage of 10 volt, this 5 volts, this 3 volts. Let me connect this here, and let me connect this here. Let me write .op, and let's see that if V0 is actually equal to what we are expecting, and the answer is yes. Okay, the answer is V2 minus V1, so 3 minus 10, so minus, yes, it is, so it is correct. Minus 69999. Now that remember that R2 over, remember that R1 over R3 must be equal to R2 over R4. Which translates so let me for instance see that if R2 is equal to 2 kilo ohm and R1 is equal to 1 kilo ohm, because I want a gain of 2, well, you just have to fix for instance R4. So R4 is equal to R2 times R3 over R1, and so basically if you decide to have R3 equal to 1 kilo ohm, then R4 will become 2 kilo ohm, just like this, to make an example of dimensioning. Now let me open a buck converter, or I don't know, a 3p1 converter, whatever circuit. So let me open a DC-DC chopper. We just need okay, so yes, this can be good. Let me run the DC-DC chopper. Let me run this current. This is just the current of this. No, this is very disappointing. This is very disappointing to read. So let me open instead a buck converter. Buck boost. Let me see. The inductor current here is low side. Yes, it is low side. This is not good either. Let me open instead. Yes, let me open just a buck boost. I don't care. So now let's put the buck boost here in this circuit here. Okay. So now let's imagine that we want to read an high side current, or even the inductor current. Yes, it is low sides, but as you can imagine. Now, as I said before, I put a shunt resistor. This is very stupid, by the way, because if it is low side, you can basically put the shunt low side and you avoid the differential configuration. So let me put a value like 10 milliohm. These are values of the shunt resistor values are 10 milliohm, 10 milliohm, 100 milliohm, something like this, something like this. So you have to also to calculate the dissipation of the shunt, which is P equal to R times I square. Remember also to design the shunt. So the shunt resistor is a very big resistor, also for these reasons. Now let me call this voltage V2. I have a problem. V2, and let me call this voltage here V1. And let me run the simulation. So this is the yes, sorry. Naturally I have to delete the everything here. So this is the inductor current. It is not filtered, it is not noisy, because this is just a theoretical inductor current. We wanted to read this current and feed it to a microcontroller, because for instance we wanted to do a current control converter. And so now the difference between V2 and V1 is not so, as you can see, it is not so beautiful as you can imagine. It is very noisy. And so it's the reading. So as you can see, even though the waveform is very clean, the reading it's not. And why is that? Well, basically because there are nonlinear elements also in here. So as I said before, you need to design a differential low-pass filter. How can you do that? Well, basically you can put a capacitor in between of 10 nano. You have to be careful because you can, if the low-pass filtering is so strong, you can even filter some unwanted frequencies. You have to be careful here, but with just this random filter here, you should be able to see something more cleaner than this. So let me just put 1 nano. I'm doing randomly. Let's also place some resistor, 1 ohm, 1 ohm, so that we can make so as you can see, there is some filtering now. This is V1 and V2. and this is the difference of V1 and V2. So as you can see, now it is entering what I'm really this doesn't make any sense. So maybe it is the op-amp which has not the okay. It may be also the op-amp which has not exactly the characteristic that we need. So I will just increase. But by the way, this is very strange. So remember that always to put the differential filter like this, so that the voltage entering will be much more cleaner. Maybe I just inverted. Okay, it has some spikes, but if you cancel these spikes with another low pass filter here, we just put again 10 nano. Okay, so the filtering is becoming quite good. No, 10 pico is too much. Okay, we are very near to the. I'm doing this with try and error. No, this is too low. So I think that 10 micro is quite what we should be seeing. So there is some filtering because the op-amp is not so fast. But by the way, this is how for instance you should design. For instance, this is how you should design your measurement stage. So you can even put yeah, this is the resonance elements. You will probably see something like this. So just add another low pass. Just add another low pass filter. 1 kilo ohm 10 nano, and you should be good. I'm retarding too much, so let's put just 1 nano. Yeah, and that's good. So as you can see, this is the input. So this is the input voltage, and this is the output voltage, which is being filtered. So there is some kind of attenuation. It is because I didn't design exactly this filter. Okay, now it is correct. The waveform is a little bit translated because, of course, there is the phase distortion of the filter. But as you can see now, we have finally achieved a very clean waveform. Now, just invert these two because we don't want to have the inverted voltage. Okay, so this is the waveform that I'm reading, and this is finally the. So as you can see, there is still some noise because, of course, you can't pretend to have exactly the waveform. If you want to do that, you should put active filters. But as you can see, we are very near to what to the original wave to actually the original waveform is. So we can consider this video over because I started. So remember the steps. I started by putting just this, just V2 and V1. So this was the initial waveform, and it is an absolute mess. So the first thing that you're gonna do is to put a pre-filter. So this is the first stage. Then you pre-filter with this, and you have just a cleaner, a way cleaner thing. Now, um, now the output voltage, which is still noisy because the op-amp has its problems, and the filter at the end. And you, as you can see, you are reconstructing correctly the signal. Yes, there are some spikes, but it is very, 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 very clean. Now I also want to show you the so-called INA. The INA is a differential op-amp already designed with integrated electronics. So we will make a compare if this INA is working. Let me put this INA because it is better. So let me do. We will make a comparison between these two, and we will analyze this. So let me put V plus. Let me open another schematic, by the way, and so let me open all of this. Okay. And this time I will not be designing everything. I will just use the INA. So the INA is basically all of this. But already integrated. So the question is, question mark, will the INA perform a better differential reading than the designed op-amp? Well, the answer is yes, but we will see that you will still need this filter here. So if I search on Google INA 232 datasheet, you will discover that these are ultra precise differential op-amp. But if you read carefully the datasheet, which I'm really showing you right now, the constructor itself will suggest you to perform a filtering. As you can see, there is the filtering which is very, very suggested. Input filters are not required for accurate measurement using the INA. But if you want to do it, these are the formulas that you need to design the correct filtering. So let's not use the filter and let's see if the measurement is good. So let's use V2 as in plus, and let's use V1 as in minus. And let's analyze the input voltage. Let me run the simulation. Could not open the file library. No. My disappointment is immeasurable. This is not so beautiful. Let's see if I can download on time this INA. But basically the result was the same. Why it is so slow? Okay, let me see if they have. Okay, they have the SPICE model. They have the SPICE model of the INA. See? I don't care. Okay, so this is the INA. So let me generate again for the INA 293. Okay, so I created this. Now let me use the INA. Let me call it auto-generated, and let me search for the INA. Sometimes LTSPICE is very buggy. Ah, okay, now the INA is here. And it's not here. So let me save this as a test. Sorry for this. Let me close it. This is because LTSPICE is sometimes is very buggy. So let me close LTSPICE. Let me close this. Let me open LTSPICE again. Let me open the test. And we will find the INA. Yes, thank you. And now it should work. Oh my god. A2. Okay, now it is working. Sorry for the wait. Now it is working. So we have, again, we have as an input voltage we have this. As an output voltage we have, wow, something incredibly noisy. So something which is not correct. Okay. So again, you need the differential filtering, as I said before. So let's do it. So let's do it again. You put some resistor, 2 resistor here, 1 ohm and 1 ohm, and you just put the input capacitor of 10 nano, and you connect it like this. So let me do it again. Okay, this is the okay, so this is the 2 voltages, and this is the input voltage. So the input voltage is already way cleaner. Don't know why it is this. It is this. I don't know why the waveform is like this. I don't want that I messed up the configuration. I shouldn't have inverted the configuration, because if you make it wrong, the output voltage to be 0 exactly. So now the configuration is correct. Don't understand why. Maybe because this INA is not good. Probably because of that. So anyway, the video has ended. We can end the video here. The INA are way much better than the one I choose. So thank you guys for following until here, and let me know in the comments if you understood everything. Thank you guys.